going to go on with pendulum, and then we're going to continue to more general rigid object motion. Can you guys in the last 5 rows, come up front, please? Okay. So last time we had this situation where we have a hinge, something's connected like this. We have a pendulum, which is something like this. It's got a center of mass someplace. We can call this point O or C or whatever we want. We call this point G. We associate with this pendulum the key distances that are involved are the distance from the hinge to the center of mass, G. We're going to keep track of how much this thing is swinging by this angle theta. We can put on the side some coordinate system. You don't have to pick this strange down and sideways one, but it makes it so you can use polar coordinate formulas without thinking quite so hard. And associated with this thing, we have some mass, and we have some moment of inertia about the center of mass, and we have also gravity pointing down like this, and this is enough to figure out all the different things we want for this problem. Let me draw a free body diagram of this thing. And I'm going to draw a funny free body diagram in that I'm going to try to anticipate the more about the free body diagram than I have a right to anticipate. But the reason I'm going to do that is because I want to give you a puzzle problem. So we have these key directions here. And properly, we should put at this point O, we should put just some reaction force like this, say ROY and ROX, and we don't know what they are. Or we could put some vector here like this, R, and that implies we don't know what it is, because we really don't know what this force is until after we've done the calculation. And we got that thing working. What was the trick? That's advanced engineering. Okay. So we really don't know this force until after we've done the problem. It's a mistake, as a rule, to try to anticipate this. What we know is that this point is held from moving sideways, so there must be some force to do that, and it's held from going up, and there must be some force keeping it from doing that. Or another way to think about it is it's held in place, so there's an arbitrary force. So either way, this is the proper thing to do. But when we're all done, we're going to calculate some force, and that force will change with time as this swings along. So let's say we've got this pendulum swinging back and forth, and to make it a little more real, you can imagine that there is a pendulum swinging back and forth. Advanced high-tech demonstration. Pendulum swinging back and forth. And you can watch it in slow motion. And as it's going back and forth, there's free body diagrams changing in time also. So there's a movie of free body diagrams where you see in the movie a gravity force here going like this and forces up here. Could be arbitrary forces, but now there's some real forces, so there are x and y components changing in time, or a single force whose direction is changing in time as it swings back and forth. We stop that movie at some instant, and that's the instant drawn on the blackboard. And we draw the force, and we draw an arrow in the direction of the force. And we might think that the arrow is up, because it's being held up like this. Or we might think the arrow is in that direction because it's being pulled back that way. Or we might think the arrow is in that direction. Or we might think it's in between in that direction. Or we might think it's over here in that direction. And here are a bunch of options for what we would see in that video. So let's say we label these A, B, C, D, and E, and we ask the question, what does this reaction force, which we don't know what it is unless we do the mechanics calculation, what is it? A, B, C, D, or E? And let's just imagine you have, say, 3 minutes to talk to your friend to try to figure that out. Now, let me just tell you, different quiz questions are different in this class. Sometimes they're things that, oh, you should be able to figure it out trivially from the last lecture. And sometimes they're things that you think you know, but I know that you don't know, so I make you get the wrong answer, like some of those pulley questions. And sometimes they're hard. This one is just hard. So it's not something that you should be able to see immediately. You actually have to think hard to do this. So don't look for a quick answer. You have to think hard to figure this out. So I'll give you 3 minutes to work on this. You understand the question? Any questions about the question? Okay, now I'll keep track of how far along you are in here by how many votes you register. Is there anything unclear about the question? You guys in the last 4 rows, can you come forward, please? You're sick? Okay. We'll take that excuse. Repeat the question. Can we have a little quiet just for a second? I'm going to repeat the question. This thing is swinging back and forth. At some instant in time, we look at it. Doesn't mean we hold it still. It means we look at it at this instant. At this instant, there's a force of gravity on here, and there's a force of the hinge on here. And the question is, what is the direction of the force of the hinge on the pendulum at this point in space, at this point in time? Is it vertical, horizontal, along the stick, between the stick and vertical, between the stick and horizontal? That's the question. Who asked the question about the question? Did I answer your question about the question? Okay. Okay, now make noise, please. Make lots of noise. I think of as cannot be determined, or none of the above. Both of those are not correct. I visited a small college last week while you were on vacation called Gettysburg College. And when I was there, I visited a class in a classroom about this size. And all of the students were in the middle section in like the first 12 rows, and every other seat was blank. And I thought, I wish I had the power over my students that you have over your students. It's just nice to have everybody up close. I think, let me just take a, who like knows what I'm talking about and thinks I'm not crazy that I want people up close and dense? Who does not know what I'm talking about? Okay. It's a psychological thing. It's a theater thing. It's a group dynamic thing. It's just how the room feels. Okay, 5 seconds left. 1, 2, 3, 4, 5. All your votes are in. And there's what you voted. Okay, would anybody like to speak in favor of any of these things? Let me just take another vote. Let me hide this one. Let's see, how do I hide it from you? I hide it from you. That's complicated. Is there a video mute button? Because if I unplug it, it screws up the whole thing. I can put something in front of the projector. I'm going to burn something out. Okay, so I don't want you to see what the right answer is. And then I want to go on and do another vote. And I only want votes from people who are confident. They really feel like they're right. Like this guy thinks he's right. No, but you think you are. You feel like you are. So if you feel like, I know this one, it doesn't mean you are right. You're allowed to be wrong. Okay, just 5 seconds. 5, 4, 3, 2, 1. Okay, so let's freeze that one. Now, of those people, can anybody put into words what you thought? Yes? You thought B, yes? So his argument is that in a simple pendulum, which would be the same problem if the stick had no mass and we put a point mass right at the center of mass, in a simple pendulum, the force has to be along the string because we just have a point mass and the sum of moments about that point mass has to be 0, right? Anybody have a problem with that? So for a simple pendulum, the force has to be along the rod. Agreed? Then he says this is not a simple pendulum, therefore something must be different. And then what do you say had to be different? So something has to cause this thing to turn, and this doesn't cause it to turn. And a force like this, which is what we have in a simple pendulum, doesn't cause it to turn. And then so you need one of these A, B, D, or E, and how did you select from those? If it's in that position, it's going to want to rotate that way. What do you mean by wanna? It's like got feelings. It's like the thing about the classroom. And if you started at that position, you could calculate out. Okay, but what quantity are you saying is that want to? That thing you would calculate is what quantity? No, but you said the want to is. How do you know the moment is that way instead of that way? What quantity would you calculate to figure that out? Okay, anyway, anybody else want to argue for B or A or C or D or anything? Yes? If you think of it as what? Yes. Yes. Now that is also true if I had just a point mass, which I've been working on while we're talking. If I didn't just think of I have a point mass pocket knife, so it fits in the new FAA rules of less than 2.36 inches. It's only 0.0 inches. It's exactly a point knife pocket knife. So it's over here. And what direction do you think the force is here? You're saying if there was no gravity, it would be in that direction. And with gravity, what's the direction of the force up here? Okay, all in favor of that reasoning? All opposed? Okay, what's wrong with that reasoning? You know, okay, so you remember that for a point mass, it's that direction. So remember, if we take for this system, draw a free body diagram, take sum of moments about this point, there's no inertia out there, so the rate of change of angular momentum is 0, so the force has to pass through that point. Or another way to say it is the string is a two-force body, and a massless two-force body, the forces have to be equal and opposite and along the string. So for a point mass pendulum, even with gravity pointing down like that, the force along the string is along the string. It's in that direction. So the free body diagram of this thing, this point mass, this FAA legit knife with 0.0 inch long blade is like this. One force down here, one force along the string here. That's the free body diagram. Fingers are force vectors, right? So that's not right what you said. Are you happy with my total insult of your brilliant idea? Okay, any other thoughts? Anybody want to argue for E or D? These are supposed to be people who are confident. Part of confidence is expressing it. Yes? I feel like it would take a long time on a couch for me to understand what you're saying. I didn't quite get that. Certainly I think I'm going to just let that one slide, but we can talk about that later. Okay. Any other ones? Okay, so let me tell you what I think, and it's very close to what you said, but I just didn't quite like your language. And you can say, that's what I said. Oh, you're just saying back to me what I said, and you're probably right. Okay, so I'm just going to say back to you what you said. But let's forget the point mass, and let's just work with this problem all by itself. Okay, we have this problem all by itself. What can we figure out is if we take angular momentum balance about point G. Now let's start out with angular momentum balance about point O. Angular momentum balance about point O is going to imply that theta double dot is less than 0. Or we could say that the omega vector, the omega dot vector, is in that direction. Why is that? Is we take angular momentum balance about this point. This has a torque. That has to be the rate of change of angular momentum, which comes from the motion of this thing. So this thing has to have an angular acceleration in that direction, which corresponds to theta double dot being less than 0. So that's the thing about want. Want is the quantity, theta double dot. Theta double dot is clockwise. Theta double dot is less than 0. That's what I was trying to get you to say. Okay? So we know from angular momentum about this poly that even if it's swinging up or swinging down, we get this result that the angular acceleration is in this direction. Whether it's still, we're letting it go from rest, it's swinging up or swinging down, it's accelerating this way. Okay. Now, if we take angular momentum balance with respect to G, now we look at this point, and we know already that it's accelerating this way. There has to be some torque causing that. So that means that this force up here has to be somewhere in this half plane. So that tells us that when we draw this picture here, that the force has to be somewhere in this half plane. Now, you got to Cornell by being good at SATs, and this one's not allowed because then there wouldn't be anything to cause this angular acceleration about this point G. Something has to cause this angular acceleration about G. I gave you a multiple choice question. I didn't give you any of these options. And I told you that the right answer is up there. So by SAT reasoning, you know it has to be one of these two. Now, if you don't like SAT reasoning, we'd like to do better than that. Well, if we look at linear momentum balance, what we get is that the force on this thing has to equal the mass times the acceleration. What is the acceleration? Well, the acceleration has two parts. It has one part associated with r theta dot squared, and it has another part associated with r theta double dot. So this is r is minus r theta double dot because I've drawn the arrow here. But just skipping the confusion about minus times the thing drawn in the wrong direction, we know that the acceleration due to the circular motion is in that direction because the theta double dot is in that direction. So the acceleration is the sum of these two things. It's something in this direction. And it's certainly something with a negative, in our coordinate system, j component. So the acceleration in the y direction is less than 0. So the linear acceleration is in that direction. Therefore, we can eliminate of these all but b. So the answer is b. Now, that's literally hand-waving argument. I mean, if you ever saw a hand-waving argument, that was a hand-waving argument. I did it by waving my hand. So if you doubt that, you can do a calculation how is the calculation? You mix and match these equations. Up to 3 of them are independent. You can use this one and this one, this one and this one, these two and one of these two, and angular momentum balance about a third point that's not on that line. And you have a set of equations, and you have 3 unknowns in those equations, and the 3 unknowns will be theta double dot and the 2 components of this reaction force. So you can, if you don't like the hand-waving argument, you can go through all the calculation to do it. But I'm doing the hand-waving argument because I'm trusting that you will learn how to do the algebra and let you take advantage of sort of this intuitive reasoning, which I can offer to you. Any questions about that? Did I say back to you exactly what you were thinking? If I'd been too pedantic and nasty, you would have said, but that's what I said, right? Okay. I've known how to do this problem since before you were born. Okay, any questions about this? Yes? Say again? Okay. This is the linear momentum balance equation. It turns out that we can use this equation this direction rather than this direction because at this point we have implicitly figured out the acceleration. Why is that? Is from this equation, and I did this last lecture in detail, we figured out what the angular acceleration was. And we got theta double dot equals minus mgd sine theta over I plus md squared. That was exactly what we had. But we figured out by just waving our arms that sum of moments about this point is in the clockwise direction, and that means theta double dot has to be that direction. So now we know theta double dot. Implicitly, we know the acceleration. What's the acceleration? Using the polar coordinate formulas, there's an r theta dot squared in that direction, which has a negative y component, and an r theta double dot in that direction, which has a negative y component. Remember, y is that direction. So the acceleration has to be somewhere in that direction. That means the net force has to be somewhere in that direction. Who asked the question? Did I answer your question? Yes, no? Not really. This picture again? We know what theta double dot is. And we know theta double dot is negative, or if you want, we know the angular acceleration is in the clockwise direction. We know what the radius is, therefore with polar coordinates we can calculate the acceleration. Actually, we have to know theta dot also. But we pretend always when we do dynamics that we know theta dot. And at any rate, the acceleration due to theta dot doesn't depend on whether it's positive or negative because it's theta dot squared. That's the centripetal acceleration. So the acceleration is a sum of 2 terms in the polar coordinate formula, one in that direction, r theta dot squared, and one in this direction, which is the r theta double dot. And it's pointed that way instead of that way because theta double dot was negative. Therefore, the net acceleration is the sum of these 2. Both of them have negative y components. Remember, that's the y direction. Therefore, the net acceleration has a negative y component. Therefore, the net force has a negative y component. Therefore, this reaction force has to be somewhere in this half plane. Do you understand that now? Yes, no? How many people understood what I just said? Raise your hand. How many did not? A few, I guess. So you ask your friends, and if you can't figure it out, then you come to office hours. Any different questions? Okay, so now we'd like to go on to a different problem. By the way, if you say you just don't like all this intuitive arm-waving argument, that's okay. You can say, I'm not one of those kinds of people. I'm one of these kinds of people. And you can sit there and grind it out. So if you're uncomfortable with intuitive arguments, make sure you get good at these arguments. And best is if you're good at both, then you can compare one to the other. Okay. So I've got a spring here, and I've got some object which is not a point mass. So this is not, if this was sharp on the edges, it's not FAA approved. It's a finite object. And I'm interested in how this thing hung by this spring. And I'm only going to do this in 2 dimensions. So I've got to get the spring sort of untwisted. And I'm interested in this thing, how it can move around. Well, it could bounce up and down, and then it's just sort of a one-dimensional problem. But, yeah. You take a couple studs back too, buddy. Okay. So I'm here back up against the wall. And this thing's bouncing up and down. And it's also doing this thing. And it's also doing this thing. And it's doing all those things at once. And we're in a 2-dimensional world, so maybe it's good to be up against the wall. So I want to know how this thing moves around in 2 dimensions, assuming it's got a frictionless constraint from the wall holding in place. It's not just a pendulum. It can do all kinds of crazy things. Okay, so I'd like to know the motion of that. Now, this one, I just tell you at the outset, is not one that you're going to get the solution with pencil and paper. It's not going to be sines and cosines. All we can do is hope to get the differential equations and put them on the computer, and then use the computer graphics, which you hopefully know already, and which, by popular request, I'm not going to explain to you in lecture, and draw a computer animation of this thing. Okay, so here we have this example of a 2D rigid object in space. And what do I mean by in space? I mean in 2-dimensional space. I mean it's moving around in the plane. It's not just hinged some crazy way. And we're going to say it's a block suspended by a spring. By the way, that last problem, more of you got it right than I think have gotten that right in previous years. So good for you. Okay, so we have this problem like so. We're going to suspend this thing, and I'm going to have a spring like this, and it's going to be connected to this block, which is going to be at some crazy angle like this. And it's got some thing like this, and it's got some reference point here. So I've got a point B, I've got a point O, I've got a point G. I've got some distances I've got to worry about. For example, this distance is going to be D. I've got, well, do I have to worry about the width of the block? I could worry about the width of the block and call it 2W. Or I could say, on the side, I've done some calculation, and I know what the mass of the block is, and I know what the moment of inertia is about point G. Now, there's this whole issue of calculating moment of inertia, which is for sure something you had practice with for area moment of inertia in TAM 2020, and is for sure a homework problem you had in Math 192, or the equivalent if you placed out of it, and it's reviewed in the book, and I'm not going to spend any time on it. So the actual calculation of this thing I'm going to assume is a skill you walked into the class with, or that you will review. But let's say we know this mass. If we know it's uniformly distributed, we can calculate the moment of inertia of this thing. Does anybody happen to know the moment of inertia of this thing? If I give you this W and this D? There's this, do you know what is it? It's got cubes in it, fourths powers, squares in it, depending how you do it. But if you do it's the mass times the distance, this total distance squared divided by 12 plus the mass times this distance squared divided by 12. It's the sum of the two results that you had in math in TAM 2020. In TAM 2020, you're only interested in this moment of inertia. Here, we're interested in this polar moment of inertia. So this would be a polar moment of inertia calculation. But in TAM 2020, you never did polar moment of inertia of rectangular things. You only did polar moment of inertia of round things. Why is that? Is because the particular strength of materials calculation is only applied to round things. But if you go back to your calculus book, you'll see that that there's something called the perpendicular axis theorem that says the moment of inertia about this axis is the sum of the ones about this axis and this axis. So you do your 20/20 calculation this way, you do it that way, and you add up the two results. Okay, so we have this thing like so. We can keep track of various things. Let's just say we pick a coordinate system like this with an I and a J. We can call this direction the Y direction. We can call this direction the X direction. And this spring has some constant, and it has some rest length L0. And our goal is to find the equations of motion for this thing. Now, it looks complicated, but if we pull it apart bit by bit, it's not that bad. So how do we pull it apart bit by bit? Is we imagine at some instant of time, we know where this thing is, and we know how it's moving. So we imagine we're given a bunch of parameters. So what are the parameters we're given? We're given G, we're given L0, we're given K, we're given M, we're given D, we're given IG. Anything else from that picture over there I didn't put in? If we needed it, we're given W, though we're not going to need it. Anything else that I left off over there? I forgot to draw G, because this thing is going to swing around. And I forgot to say what we're trying to do is we're trying to find the motion. Let's put that as a question. So we're given a bunch of parameters, and we're given the present so-called dynamical state. What do we mean by the dynamical state? Is we're given all the positions and the velocities. Now in this case, what are all the positions and the velocities? Well, they're the position of G. And that, remember, when we write that, that's always a shorthand for the position of G with respect to O. And we're given the velocity of G. And we're given the angle. And what angle is that? Well, it's going to be the angle of the object. So a missing thing in this picture is that we're going to keep track of the orientation of this thing by, say, some angle here, theta. And we're also given theta dot. So now we'd like to know how this thing moves. That means we'd like to know how these things change in time. How are we going to figure out how they change in time? We're going to write differential equations, and we're going to solve them on the computer using Euler's method or the midpoint method or RK45 or RK23 or ODE 115S or whatever method we want. We're going to use our crystal ball. Our crystal ball is going to be something that, given the rates of change of these things, tells us how they advance in the future. Given that we know how to calculate the rates of change from these numbers, we can go forward and so on. So this collection of things, when we go to do this in MATLAB, this collection of things is what we're going to call Z. It's going to be a long list of numbers. 1, 2, 3, 4, 5, 6 numbers to describe this thing. 3 numbers for position and orientation, and 3 more numbers for velocity and angular velocity. Okay, so our goal is to find from these things RG dot, VG, theta dot, and theta double dot. Now, VG dot, theta dot. Now we can make this a little less confusing if we call this thing omega, and then we don't have the trivial result looking quite so trivial. So our goal is to find this list of numbers. Therefore, this whole collection we think of as Z dot, and this then we can solve with on the computer. So this is the overall logical setup. Now, Once you've got that straight in your head, then you're ready to do what this course is about, which is to figure out these things. That's what dynamics is about, is to figure out these things. And then math is about solving the differential equations if you can, but you can't for a problem that's hard like this. Any questions about this setup? Anybody want to repeat anything about that? Okay, so first we have the kinematic easy parts. And those are that r dot of g is equal to vg, and that theta dot is equal to omega. So these are 3 of our 6 ODEs. So half of what we need to give to MATLAB is just trivial. So now we're getting down to the hard half. And the hard half is the part we have to use the laws of mechanics for. Now there's a law of mechanics. The Zeroth Law of Mechanics is a legal law, not a mechanics law. Now you guys who came late and sat in the back, don't do that. Today we let you go, but please sit forward. And it's that we have to draw a free body diagram before we try to do any calculations using the laws of mechanics. So what's the free body diagram look like for this thing? We've got this block. We've got this point G. We have mg here, and we can put mgi, and therefore we don't have to multiply by this unit vector. And we've got some force here, and we've got some tension force, and it's not parallel to this block. It's just a tension force in some direction. And I'll just call this F. And now we're going to have to calculate what that F is. Well, here we have this point B. And what is the force F? It's a force which is the tension in the spring times a unit vector from B to O. So it's a tension vector times a unit vector from B to O, and that's the negative of the unit vector from O to B. Now we have to do some geometry to figure out what that is. So one thing is we have to figure out what is this O to B, lambda O to B. That's the position of B divided by the magnitude of the position of B relative to O. Then we have to figure out what this tension is. That tension is equal to K times the change in length. But what's the change in length? The change in length is equal to the present length minus the initial length. But then what is the present length? The present length is equal to the magnitude of the position of B with respect to O, which is the position of the vector B. So that looks pretty good in terms of figuring out this force. That means we now know what this force is, if only we know where B is. But that means we have a side calculation where we have the position of B, which is something we have to figure out also, because the position of B was not given to us explicitly right here. Position of G was. So what's the position of B? It's the position of G plus the position of B with respect to G. Then we have another side calculation, is what's the position of B with respect to G. So now we go back and look at this picture, and we see, oh, it's over there d sine theta in the minus j direction. Is minus d sine theta j. And then it's also a minus d cosine theta I. Now, if we try to write this as a formula, this will turn into a giant mess. Why is that? Because to do this, I've expanded this out in one direction, but to actually calculate it from the given things, we have to go in the opposite direction, which is a usual thing, that the order of thinking and the order of calculation are backwards from each other. So first, given r of g, we have to calculate this r of b with respect to g. This has these two components. Then we have to add that to r of g, which is given. Then we have to calculate this length. Then we have to subtract to get this delta L. The k we already know. Now we've got the t, but we have to do that same substitution in here, divide by this same length again and substitute it into here. And then we finally get a formula for the vector, which is that force. So given rg and given all the parameters, we can calculate that force, rg and theta. OK, so to finish this problem, then all we need is the angular momentum balance equation and linear momentum balance equation. So we take linear momentum balance. And the linear momentum balance equation says the sum of forces is equal to the mass times the acceleration. And what are the sum of forces? It's this thing we called F. Let me just call it F spring so it doesn't look too abstract. There's F spring. There's plus mgi, and that equals m times vg dot. So this is one equation which we now know how to evaluate. This is ready to plug into MATLAB. Because we now know, we can write this again, I guess, like this. Vg dot is equal to F of the spring, which we know, plus mgi, which we know, divided by m. Then we also have angular momentum balance. In this case, the easiest angular momentum balance equation to use is the one about the center of mass of the object. And this says that the sum of moments relative to the center of mass of the object equals the rate of change of angular momentum relative to that center of mass. What is that sum of moments? Well, it's the position of b with respect to g crossed with fs. And we know both of these things. And what is this thing? This is theta double dot igk. Therefore, we can solve this to get theta double dot. To do this, we have to do this cross product. This cross product involves this complicated thing. This one's not so bad, just a sine and a cosine. And this thing, which is a giant mess. We can try to do all that stuff with formulas. But if you're going to do this on the computer, you don't have to. You just, in sequence, calculate all these things at every step in time. And therefore, we can calculate the evolution of this in time. Once we've got that, we've got theta versus time, rg versus time. We can animate it, because we can take the object, and we already know how to rotate them. And then if we've got the position, we can add to all the position vectors a constant, which is a position. And then we can get an animation of this thing moving around on the screen. Does anybody feel insecure about any step of this reasoning or calculation? So it's a complicated, messy problem, but this is the incredible thing that in just 8 short weeks, you now know how to do this kind of problem, which probably you couldn't have imagined doing beforehand. You could have imagined doing it beforehand, but you can now, yes? Cool, right? Horrible thing that you learn something in school. I hope, anyway. OK, so ask questions in office hours. See you Tuesday.